Welcome everyone. Thermal cloaking and invisibility technology have been dreamt of for decades, often confined to science fiction and fantasy. However, real-world research has brought us much closer to making invisibility practical. At the center of these developments are metamaterials, which are engineered to manipulate energy in ways that natural materials cannot. These materials do not rely on their chemical composition, but instead depend on their internal structure, which is designed to interact with various forms of energy, such as light, heat, and radio waves. Metamaterials can be designed to redirect these energies around an object, allowing it to appear as though it is not there. This kind of cloaking is not just for visible light. It includes thermal cloaking, radar invisibility, and even experimental work with sound. The key principle is that the material creates a path for the energy to travel around the object, effectively hiding it from the sensors that would otherwise detect it. While the technology is still in development, it is advancing rapidly, and functional invisibility may soon leave the laboratory and enter the real world. Thermal cloaking refers to making an object invisible to thermal imaging devices, which detect infrared radiation emitted by warm objects. Every object that has a temperature emits this radiation, and thermal cameras can see it. To become thermally invisible, the object must not reflect or emit heat in a way that the camera can detect. Instead of blocking heat, thermal cloaking materials guide it around the object. To do this, engineers design layers of materials with different thermal conductivities. These layers force the heat to flow in a specific way, curving around the object and continuing on as if nothing were there. From the perspective of a thermal camera, the background temperature appears undisturbed. This effect has already been demonstrated in laboratory experiments using materials like copper and rubber, arranged in carefully calculated patterns. Radar invisibility is another practical application of cloaking technology, and it is already being incorporated into modern defense systems. Radar works by sending out radio waves and detecting how they bounce off objects. If no waves bounce back, the object appears invisible to radar. Traditional stealth aircraft like the B-2 Spirit use sharp angles and radar-absorbent coatings to reduce their radar signatures. Metamaterials offer a new and more versatile solution. Instead of absorbing or deflecting radar waves, these materials bend them around the object and guide them to the other side. To the radar system, it appears as if the waves have passed through empty space. This allows for much more freedom in the shape and design of stealth vehicles. Researchers are working on metamaterial coatings that can be applied to aircraft ships and land vehicles, making them less visible to radar without the need for bulky or angular designs. These technologies are being tested in real-world military systems and could become standard within the next 5 to 10 years. Their advantage lies not only in improved performance, but also in flexibility and weight. Metamaterial radar cloaks can adapt to irregular shapes and require less space than traditional stealth structures. This opens the door to new generations of drones and unmanned vehicles that can travel unnoticed through high surveillance areas. The most difficult form of cloaking is invisibility to visible light. Light has a much shorter wavelength than heat or radio waves, which means the metamaterial structures must be extremely small and precise to interact with it correctly. This presents significant engineering challenges. Even the slightest irregularity in the structure can prevent the material from bending light effectively. Despite these obstacles, scientists have created metamaterials that can make small objects invisible to light in very narrow frequency bands and under controlled viewing angles. These early successes are limited in scope, but demonstrate that the concept is sound. Researchers are now exploring the development of active metamaterials, which can change their properties in real time using electrical signals. These materials could adapt to different lighting conditions, viewing angles, or sensor types, making them far more practical than their passive counterparts. If these systems can be made reliable and scalable, they could form the basis for invisibility clothing, advanced optical camouflage, and new forms of augmented reality displays. Practical uses of cloaking technology are much closer than full optical invisibility and could be deployed in commercial and industrial settings in the near future. In hot climates, thermal cloaking could be used in building materials or outdoor shelters to redirect solar heat and keep interiors cooler. Firefighter uniforms could include thermal cloaking layers to protect against radiant heat. Sensitive electronics in data centers or spacecraft could be shielded from temperature fluctuations using cloaking materials. In aviation, radar cloaking could reduce interference between nearby aircraft and allow for safer air traffic management. Even partial invisibility or reduced detectability can provide significant benefits in safety, energy efficiency, and equipment lifespan. Consumer-facing applications like privacy windows or adaptive visual displays that change based on viewing angle are also being explored. These are achievable goals for the next 5 to 10 years and could enter the market well before full-spectrum invisibility becomes possible. Beyond practical use, cloaking raises complex questions about ethics and regulation. The ability to become invisible or undetectable to sensors could be used to avoid detection by law enforcement or public surveillance. This would make cloaking attractive to criminals or hostile agents. Questions arise about who should be allowed to possess cloaking technology and under what conditions. Governments may need to classify advanced metamaterials as controlled substances, similar to how military-grade encryption is regulated. Civil liberties groups may also raise concerns about privacy if cloaking becomes widespread in commercial or consumer settings. Legal systems may struggle to keep up with technologies that allow people or machines to operate undetected. For example, should it be legal to use cloaking materials in public spaces or in vehicles? What happens if a cloaked vehicle causes an accident? These are serious concerns that will need to be addressed as the technology becomes more capable and more available to non-government users. Researchers are exploring cloaking not just for heat, light, or radar, but also for sound and vibration. Acoustic cloaking materials can redirect sound waves around an object, effectively muting it or making it acoustically invisible. These technologies could be used in industrial noise control, urban planning, or even personal sound isolation. In the medical field, cloaking could lead to more precise thermal imaging by isolating background heat. Surgical tools might use localized cloaking to prevent heat damage during laser procedures. Cloaking technology is moving steadily from theory into application. We are witnessing the early stages of a new class of materials that can manage visibility across multiple forms of energy. While perfect invisibility remains a long-term objective, partial cloaking is already proving useful and achievable. As metamaterials continue to improve in precision, durability, and responsiveness, we will likely see an increase in real-world products that feature cloaking properties, whether for defense, medicine, infrastructure, or everyday tools. The concept of invisibility will shift from fantasy into engineering. It will not be about vanishing entirely, but about choosing what is seen, what is sensed, and when. This kind of control over visibility and interaction will reshape how we design technology and how we move through a sensor-rich world. Thank you very much for watching. Please like and subscribe.